So any questions? Okay, so then let's start from where we left off. Yes. So voltage actually in the context of waveform is you said that it's actually some greater than between. Okay, continue. Okay, you mentioned that to the other way. That essentially is the depth. So let me address that. So there's a difference in terminology. Let me rephrase his question. Whatever he is asking, then let's take it from there. So this is a brief revision of what we were doing in terms of the architecture of the MOSFET. So let's call this as a source, and let's call this as a drain. And the voltage that I'm applying between the source to drain is VDS. And let's assume that the body is grounded. And this was the gate. And the voltage between gate and ground, let's say, is VGS. Okay. So then we saw that if we apply a voltage VGS greater than threshold voltage, then we will accumulate electrons, mobile electrons there. Okay, let's see. So we'll accumulate mobile electrons there. And this is a good thing because ultimately we'll be able to use these mobile electrons for the transport, right? We'll be able to use these mobile electrons for flow of current between drain to source. So now what happens when you apply certain voltage between the drain and source? So not only that these electrons will flow this side, but essentially the current will flow from drain to source. But in the process, when you are applying a drain to source voltage, the rectangular slab of electrons that I have drawn in the channel will no longer remain rectangular, right? So what will essentially happen is this slab will taper, right? This slab will taper simply because you can think of every portion of this slab as a small section of a MOSFET itself. And the charge underneath this channel in that sliver for this small MOSFET will be proportional to the voltage difference between the gate and the channel, right? So now the voltage at the gate is VG, voltage at this channel, at this particular sliver, let's call it Vx. So since the voltage across the channel is Vg minus V of x, so it makes sense to argue that the mobile charges in the channel, in that particular sliver of the channel, will be proportional to Vg minus Vx. And if Vx is higher, then the channel charge will be higher or lower? Lower, right? So if Vx is higher, the channel charge underneath that channel will be lower. Okay. But note that Vg is same for the entire part of the channel, but the Vx is not same. So that is why you'll have a tapering. So now there is a terminology issue here. The terminology is this vertical direction. It's called the depth. This is called the length, as we initially alluded to a couple of classes back. And there is obviously another dimension to this MOSFET structure, which is going into the board, right, into the projector. So which will be this side. So this width is called W. Now, as it turns out, does that answer your question? Okay. So as it turns out, for a circuit designer, the things that are in your controller, these lateral dimensions, that is W and L, you can vary. You cannot vary the thickness of the oxide, that is, it's Tox. You cannot vary that as a circuit designer. You cannot vary the doping. You cannot even vary this depth because, okay, one can argue that the depth is, you can vary the depth by applying different value of VGS, but that is not a consequence because ultimately we are in, even though I have demarcated this channel charge like a, with a finite depth D, you have to note that these are all mobile charges. So there is no reason for us to believe that these mobile charges will be spread along uniformly between from, I mean, what I'm trying to get at here is that you start from the interface and you go down. It's not necessary that the charges will be spread out uniformly as you go down, right? Because they are mobile charges. If it sees an electric field, it will go up, right? So as it turns out, you'll have most of these I mean, even though I have drawn it in a thick layer, it's not very thick. It's almost like a sheet of charge just underneath the oxygen. Okay. So for all practical purposes, this depth is, you can assume it to be close to zero. So ultimately, it's almost like a parallel plate capacitor with the top plate being the gate and the bottom plate being the sheet of charge. Now, if you put a microscope and observe that sheet of charge, there will be a profile. But that profile is not too much of consequence for circuit designers. If you are a device designer, right, for the same structure, if you are making this device, then the things that in your, then the parameters that are in your controller, everything that you see here, you can change the doping concentration, you can change the concentration of, you can change the thickness of the oxide, you can change N plus, doping of the N plus, you can change WL, obviously you can change. So you can even change the way the crystal has been made. So if you are a device designer, if you're a device engineer, all these parameters are up for grabs. You can change anything, right? Because you are making the device. But now when you have the device, you have become a circuit designer, you cannot change the device anymore. It's like a Lego, right? You take a Lego block. Now you have been asked to make whatever you can with that Lego block, right? So if you are making the Lego block, then you can decide on the dimensions, color, blah, blah, blah. But in this case, once a Lego block is made, you can only change certain aspects of it. Obviously, you can put multiple of these devices to make whatever circuit you want. But as far as the device dimensions are concerned, you can only change W and L, which means you can make either the device wider or you can make the devices longer. That's the only handle that you have. Okay. So then what we said is we will try to relate this to Y parameters, and we saw that under certain cases, okay. So now the symbol for this MOSFET is essentially this, and if we have to relate directly to this structure, the symbol should be expressed like this. This is the gate, this is the drain, this is the source. Because I want to get to Y parameters, where the input is often applied on the left side and output is taken from the right, I flip the symbol and 90 degree, and I'm trying to show it in this manner. This arrow points to the fact that it points to the fact that current is flowing in the direction of the arrow. So which naturally means that by putting this arrow, I have already implied that the drain is here, the source is here, okay? Because current flows from drain to source in this N-channel MOSFET. And this is obviously the gate. And we further said that if this is my 2-port, right? If this is my 2-port, where the source terminal is common to both the input and the output ports, then I can express this IV characteristics in terms of the 2-port parameters. Where you see the I1 is always 0 because it's going into a gate, it's going into a capacitor. So the DC value of I1 will always be 0. So of the 4 quadrants of IV that we are interested in 2 course parameters, 2 quadrants we don't have to bother at all because they are they're unambiguously 0. The other 2 quadrants that we have to worry about are I2 V1 and I2 V2. And we also derived the equation for this particular structure. And the equation was I2 equal to IDS, that is the current between drain and source, is mu n Cox W over L VGS minus threshold voltage times the drain to source voltage minus half of drain to source voltage whole square. Okay. By the way, you have to keep in mind that Cox is capacitance per unit area, not the total capacitance. Okay, great. So now, if we plot I2 versus V1, right? If we plot I2 versus V1, what we see, we should see till the threshold voltage I get 0 current, and after that I get a linear increase, right? This is for a particular VDS. So this is for a particular VDS. So this is VDS is fixed. And Y21 is essentially the slope of this line, which will be mu n Cox times VDS. And what about Y22? Or rather, what will be I2 versus V2 curve look like? This is essentially an inverted parabola and can start right from VDS equal to 0, right? So V2 is essentially VDS, and then it increases. And if I simply plot it out, it should have a maxima and should come down. And where will this, what will be, so where will this maxima be?
VDS minus VT.
Yeah, so essentially, I mean, maxima minima, you differentiate and put it to 0, right? So when you differentiate, what are you anywhere trying to get? You are trying to get Y22, right? Del I2, del V2 is essentially Y22. So your Y22 will be mu n Cox W over L VGS minus VTH minus VDS. And when you set this to 0, you get the maximum of the curve, and maximum of the curve happens when your VDS is equal to VGS. Now this is where we stopped in the previous class. Now the question is, what happens if I keep on increasing VDS beyond VGS minus VTH, right? So this curve clearly tells you that the current should drop, right? That's what this model says. But as it turns out, it doesn't do that. And the reason for that is as follows. So I hope you are comfortable with the fact that this channel charge has a profile like this, albeit not enough. This thickness is not up to scale. So now, what happens when VDS effectively becomes VDS becomes VGS minus VT? At that time, I can simply say that your VGD, that is VG minus VD, is equal to the threshold voltage, right? The source voltage cancels off on either side of the equation, and I rearrange, I get VG minus VD equal to the threshold voltage. Now, what is VG minus VD? VG minus VD points to that sliver of MOSFET which is attached to the drain terminal. Okay. So this sliver of all it is saying is that the difference between the gate and the drain voltage, or difference between the gate and the channel, at that particular sliver has reduced to threshold voltage. And by the very definition of threshold voltage, what do we know? That if it's, I mean, when VGD or the voltage between the gate and the channel is equal to threshold voltage or lower, I don't have any mobile carriers, right? So at this junction, when we reach this condition, we say that the channel is pinched off, right? It's a channel is pinched off, and when the channel is pinched off, essentially the profile of this channel charge will slightly change again. It will go to 0. It will go to 0 at the under pinch off condition. Okay, so at pinch off. Yeah, so do you agree with the fact that when VG minus VD equal to VTH, there cannot be any channel charge in that small sliver? Yes. Right? If there is no channel charge, which means we call that a condition where it's pinched off, right? It's pinched off because you can think of this like the analogy, even though it's not fully accurate, the analogy is like water flowing through a pipe. Okay, so you have water flowing through a pipe, and the tap is your gate. Okay, so you can modulate the rate of flow by changing the tap. Okay, now if you turn the tap fully off, then your water flow can stop, right? So the analogy between this analogy and the water analogy breaks here. So you can modulate the water flow by changing the tap, but here you can do that, but in that analogy you can completely turn off the water flow, but here you will see you cannot do that, and there is a reason, and the reason is water flow is purely gravitational. Here it has another aspect to it. So I mean, the analogy that I gave, it might appear that once we apply VG, if there is no channel, there should not be any channel, there should not be any current. Right. So I2 should be 0 with that analogy. But as it turns out, it's not, because note that here you have a lot of mobile charges, right? And when I2 becomes, when you have pinch off condition, what happens here? Here you have Na minus, right? Because you have depletion region underneath. You have removed all the mobile carriers, but the Na minus still persists. Okay, and since you have Na minus, which means it's not an electrically neutral region, right? You have a negative charge, you have electric field there. And what is the electric field direction?
A minus, but no mobile.
No mobile carriers, but there is electric field. So what is the electric field direction? From drain to source. So you'll have electric field, you have this electric field still persists. That this electric field goes all the way from drain to source, albeit the value of the electric field reduces, but it goes from drain to source. Which means if it finds a mobile carrier somewhere here, this mobile carrier can go through. Right? So this is equivalent to, the analogy is similar to, if you recall, in a PN junction, so this is P, this is N, and you have a reverse bias condition, let's say. In a reverse bias condition, this depletion region that we saw here you had Na minus, here you had Nd plus. There was electric field from N to P. Okay, but let's assume that you have dropped some electrons in this depletion region. How is a matter of detail? That the electrons might be generated by thermal generation process, or it might be generated because you have put and wear and dropped some electrons into the depletion region. But let's assume somehow the electrons have made it to the depletion region. If the electron somehow makes it to the depletion region, then the electrons will be swept by the electric field in this direction. These electrons will flow in this direction, which means there will be a current flow. And that was one of the genesis of the reverse saturation current, right? So this pinch, the flow through the pinch off region is similar to this, just that the carriers there are not getting generated by thermal generation. They are getting pushed into that region by the whole bunch of electrons that are there in the remaining part of the channel. So those remaining electrons are making their way to the depletion region, which we are marking as a pinch off, and the existing electric field are pulling it away towards the drain, right? So there is a current flow. I hope you agree that there is a current flow, right?
But the path through which the electrons go, it must have some steady state density of electrons.
Yes. So essentially what he is asking is, I mean, now we say that there is no electrons, but there is a current flow, which means there is electrons. There is a dichotomy between these arguments, right? So yes, indeed you are correct, but note that all these are approximations because there is no, I mean, even though when we say that it's depleted of everything, there is always electrons and hole pairs getting generated. Just that their concentration is not higher with respect to the ionized impurities. So that's why, I mean, it's basically the game of which is higher, which is smaller, right? So when you have depletion region, it doesn't mean that there are no mobile carriers. There are, but their concentration is much lesser than the ionized impurities. So as he is rightly pointing out, his question is, since my mobile carriers are moving through and I take a snapshot of the mobile carriers in that pinch off region, I should see mobile carriers, right? Then why are we seeing it's depleted? Is depleted with respect to the rest of the channel. The rest of the channel concentration of mobile carrier is much higher, but in the pinch off region, you will still have mobile carriers, otherwise you cannot have any current flow. Okay. Okay, fine. So now the question is, what happens if you increase VDS? Yes.
It would not increase the current.
Okay, yeah. So let me get back to that. So essentially what is happening is, so even before going there, let's assume that this depletion region is of finite width, right? So this pinch off region is of finite width. Let's call it del X, or let's call it del L, because I mean, this horizontal dimension we call is L, so let's call it del L. So can you comment on the relative resistance of this part of the channel and the part and the part of the channel where it has gotten pinched off? The question is, can you comment on the relative resistance? I haven't given you any numbers, so it's a guess. So can you comment on the relative resistance, right? This is a channel which has there are electrons flowing and not in zero resistance region. So you will have resistance. So what I am asking is that, what do you think will be the relative resistance between the pinched off region and the part which is not pinched off? Yes, why?
Less number of
Yeah, there are arguably almost zero mobile carriers there, right? So there are arguably almost no mobile carriers there with respect to the rest of the channel. The rest of the channel is almost metallic, right? The pinched off region is almost like an insulator, right? It doesn't have any electrons, but we are forcing electrons to flow through that channel. So naturally, from that very argument, you can argue that most of this additional VDS that I will be applying will drop across the pinch off region, right? The voltage across this voltage in this region, which is other than the pinch off region, will remain as is, almost as is. The additional voltage will drop across the pinch off region. And what is that voltage as is that is remaining across the channel? It's equal to that voltage which appeared during pinch off, almost equal to that voltage. There will be some additional drop, but with respect to the original voltage, I can argue that the voltage across the channel remains exactly equal to VGS minus VTH, because at that value of VDS, we hit pinch off. Make sense? Okay.
The drop across the channel will be how much the voltage talking about?
Okay. So think of it in this way. So if you have current flowing, from left to right. So let's model this channel as this is a channel with electrons, right? So let's model this part as this color and the other pinched off part as this color, right? So essentially, now what we are doing is we are pushing current into this IDS. Okay, so you'll have drops, you'll have two drops, you'll have, let's say, VCH and VP. Okay, by the qualitative argument, what did we infer? We are inferring that this RP is much higher than RCH, right? If RP is much higher than RCH, then almost the total drop of VDS should appear across RP. Okay, but note that this RP doesn't exist before pinch off. RP exists only after pinch off, which means it is only after pinch off any additional voltage that you apply will drop across RP. And I can argue that across RCH, the drop was whatever it was at the time, at the condition of pinch off, just at the edge of pinch off. Do you agree? So if you agree with that, then it becomes very easy to understand that the current will remain constant, because ultimately what is determining the current in the through the MOSFET is basically the voltage difference across the sheet of charge, and the sheet of charge is giving you this RCH. Okay, so this sheet of charge, if the voltage difference across the sheet of charge doesn't change, then the current, because of that change in sheet of charge, will remain constant. And what will be that constant value? That constant value will be that value when we reached pinch off. Make sense? So which essentially means that my IDS will be for the value of VDS equal to at pinch off VGS minus VTH.
So the density profile of electrons will remain the same, but just it will be scaled to a thinner one.
Yes, and something happens because of that. I'll get to that. Yes.
So like in diodes, when we it's there is a efficient.
Right.
So does that translate that over there also?
It will increase. It will increase, and that has a second order effect. We'll get to that. His question is in a diode. The analogy that I gave in a diode, if I increase this V applied, right, this depletion region will increase, right? Naturally, I mean, we know from diode analogies, this increases. Does that also happen here? In fact, it happens, and I'll get to that. There is a second order effect associated with it. But so far, so good. So far, do you agree with what we did? No. If you agree with what we did, then the channel charge, or rather the current in this region where VDS, so IDS, when VDS is greater than VGS minus VT, becomes, if I just replace VDS with VGS minus VT, I get mu Cox W by L times 1 by 2 times VGS minus VTH whole squared. Okay, and note that this is, I mean, mathematically or algebraically, I could have as well written this to be half of VDS squared, right? I could have as well written this half of VDS squared, but would that equation be accurate to express the current in this region when VDS was greater than VGS minus VTH? No, because from argument that we laid out, it becomes apparent that the current remains equal to the value of the current at the edge of pinch off, right? Which means that it doesn't have any dependence on VDS. At the edge of pinch off, you can either express it as VDS or VGS minus VTH. But beyond pinch off, if you express this current as VDS, it will be incorrect, right? Because the leap from the edge of pinch off to beyond pinch off was qualitative, right? So this mathematical model will not be valid if you replace VGS minus VTH with VDS in this equation. Okay, so this region where the current gets saturated, right? The current doesn't increase beyond VDS is obviously called a saturation region of upload. So now what happens? What is my new ID VD characteristics? So this is I2 is equal to, which is IDS, and V2 is VDS. What does it look like? It looks like it increases, then reaches a maxima, and the value of maxima we reach at VGS minus VTH, and it saturates. And the saturation current equation is half mu n Cox W by L VGS minus VTH whole square. Okay, saturation, what is the model? My Y11, Y12 anyways are 0. What is my Y22 is also 0 in saturation, right? This is in saturation. And I have Y21, V1 here. And there is a critical difference between the two-port model that we drew and the MOSFET two-port model. And the difference is the fact that the third terminal is common, right? The source terminal is common between the input and the output, right? So essentially, in case of a MOSFET, this is this. So this is the source, which is common between both the input and the output. You have gate here, you have drain here. Okay. So another piece of jargon. In Y parameters, we call this Y21, Y22, but when you are dealing with transistors or these type of devices, this Y21 is called GM, or the transconductance, and Y22 is called GDS, or the conductance between the drain and the source. In terms of resistance, this is called 1 over RDS, which is basically the resistance between the drain and the source. So going forward, we'll basically discard Y21, Y22. We'll deal with GM and GDS and RDS. Okay. So now that we have arrived at a situation where we can use this MOSFET under certain condition, not always. It's not as if you take the MOSFET and plug it in and apply an input and output, you are going to get an amplifier. You have to first massage the MOSFET and make sure that the MOSFET gets into saturation region, and then apply an input, and then you can hope that the output will be, you can get some sort of amplifier out of this contraption. So what will be the, let's assume that I haven't yet showed you how you will have to bias it, but let's assume that you have biased it. And if you have, after you have biased it, you have applied an input, let's say VI at this input port, right? So essentially what I'm saying is, let's assume you have applied an input here and you have an RL there. So what is the gain that you expect between V out and V in? This is V in and this is V out. What is the gain that you expect? Or rather, what will be V out in terms of V in? Minus Y21 V1 times RL, because Y22 is 0, right? So our gain is equal to minus Y21 RL. So now we can say it's minus GM times RL. We have to get used to this terminology. What is GM? What is the expression for GM? Yeah, but what will that be in saturation? Can calculate and tell me? Which current equation you will be using to find GM in saturation? So you have two current equations, right? One is that mu n Cox W by L VGS minus VTH times VDS minus half of VDS squared. And another is mu n Cox W by L times 1 by 2 times VGS minus VTH whole square. Which one will you use? Second one, because the second one was the saturation current equation, right? So again, the small signal model doesn't convey which region of operation you are at, right? Small signal model is just a small signal model in terms of parameters. The value of the parameters are dependent on which region of operation you are at. So whenever you are drawing a small signal parameter, at the back of your mind, you should have the wherewithal wall to understand that you are assuming that your transistor or whatever device you are using is biased in the appropriate region of operation. Okay. So now, in case of this, what is GM? GM is mu n times RL, right? So this is your gain. Maybe somebody can open the door, let it out. Got bored. Okay, fine. So what does it tell you? So note that this V out minus V, this gain, in this expression, everything is quiescent. Everything is quiescent parameter, right? Threshold voltage is a device characteristics. This VGS here is quiescent. It's not the incremental input, right? This VGS is quiescent. But the relationship, this V out over V1 is incremental. The small V out, small V1 or small V in is incremental. This gain is, by using this equation, we have been able to relate the incremental gain with quiescent conditions, right? Okay. So now what does it, from looking at this equation, what does it tell you if I am not satisfied with the gain? What should I do as a circuit designer, given that you have RL and you have controls over? So as a circuit designer, if you think that I'm not satisfied with gain, I have two knobs. I can either increase W by L or I can increase VGS, right? So let's assume that, let's think that I'll increase VGS, right? So can I keep on increasing VGS arbitrarily to get higher and higher gain? Okay. So what is the loophole? Now let me get to this IDVD characteristics. So VDS. So this equation, so when you have multiple parameters to handle, you cannot look into only what happens when you change one parameters. It can be misleading, right? Because when you change something, something else is changing in the background also. You have to understand what is changing in the background, because all these are interrelated parameters. So this equation is telling you that your gain is directly proportional to VGS minus VTH, which means I keep on increasing VGS minus VTH, I'll get higher and higher gain. But what this equation is not telling you is that this is under the condition of saturation. You have to honor the saturation region condition, right? So for that, you will have to impose another condition. What is that condition? That condition is the fact that you have to look into the IDS VDS curve. And what is the IDS VDS curve telling you? Yes. So IDS VDS curve is telling you that you always have to be in this region. Okay. And this region is VG. Let me call this VGS1. Let me call this VGS1 because for a certain value of VGS1, you have got this gain. Now I say that I'll increase my VGS1 to get more gain. If you increase your VGS1, what happens to IDVD characteristics? Let's say, let me call it, this is VGS1. Okay, so what do you think will happen to the IDVD characteristics if I increase VGS1 to, let's say, VGS2? I mean, yeah, this point will shift, but what will happen to the entire curve? Yes, so note that this curve is, in this region, it is proportional to VGS minus VTH times VDS minus half of VDS squared. And this region, it is half proportional to VGS minus VTH whole square. Sorry. So if I increase VDS, I obviously expect this curve to move upwards, right? So I would expect this curve, if I increase VGS, I would expect this curve to move. But where do I expect this kink to happen? It will be VGS2 minus VTH, right? This kink will happen as VGS2 minus VTH, which means that if VGS2 is higher than VTH, I expect that the kink to happen at a higher voltage, right? Make sense? Now, the issue is, if you have infinite room to increase voltages, you don't have a problem. But the issue is, you always have a condition that you have finite battery voltage, right? Your VDD is generally not changed. You cannot change VDD. It's generally fixed, which means that the maximum VDS that you can apply, or maximum VGS or maximum VDS that you can apply is some VDD, right? Which means this, you are limited. You cannot go beyond VDD, right? This is a system level. This is a system level constraint. We are adding constraint on constraint, right? This is what a designer's job is, to understand what are the constraints. So, okay. So generally, how are we using this MOSFET? We are using this MOSFET as, we are applying some VDS here, and we are applying some VGS here, right? And why do we need to apply? We need to apply this in order to ensure that the MOSFET is in the proper region of operation. The MOSFET is in saturation region of operation. So now one might argue that what is the value of VDS, maximum VDS that I can apply? So generally there is, for any device, there is a maximum voltage that you can apply before which the device breaks down. That is one thing. And even if we don't go there, there is certain system level specifications which will say that I cannot give you battery more than 3.3 volt, or I cannot give you battery more than 1.2 volt, right? So there is a constraint on the VDS max from a system level perspective, not from the device perspective always. From the system level perspective, generally you have a battery voltage limitation. So let's assume that you have a battery voltage limitation, which means the maximum VDS that you can apply is VDD, or maximum VGS also that you can apply is VDD, right? So now, since we are interested in this ID VDS characteristics, what I'm saying is that your maximum VDS that you can apply is VDD, which means this region is inaccessible. You cannot go there. That region doesn't exist. For the device it exists, but because you have a VDD limitation, you cannot go there. So if you cannot go there, and in order to increase gain, you are increasing VGS to do you see a constraint that has emerged?
Yes.
What is the constraint?
You cannot go deeper into the
you cannot go deeper and deeper. You cannot simply keep on increasing VGS. What is the maximum you can go? You can go till the not pinched off, till that condition where correct. So essentially you can go somewhere here, right? So you can go, what is the maximum VGS that you can apply? No, the max. So VDD will be equal to VGS minus VTA, VGS max minus threshold voltage. So the maximum VGS that you can apply will be VDD plus threshold voltage from this simplistic model, right? So which means there is a maximum gain that you can get. You cannot really keep on increasing the VGS minus VTH. VDD is the battery voltage.
The
maximum battery voltage, right? So it's not called VDD. So generally, what I'm trying to get at here is that you have some network and you have a battery, and the entire part of the network is extracting current from the battery, and the battery has some voltage, and we generally call this as VDD. So because we are using MOSFET, we call it VDD. When people use BJT, we call it VCC, but doesn't matter. You call it whatever you want, right? But the moot point here is that if the maximum available voltage that you can use is VDD, which means for a particular MOSFET, the maximum theoretical voltage that you can apply for VDS is also VDD, right? In fact, it's lesser than that, but we'll get to that. But this is, at least from this argument, we can, we should be able to appreciate that the maximum gain that you can get from this, theoretically, the maximum gain that you can get is limited, and that is equal to this mu n Cox W over L, VGS max minus VTH times R. Yes. Can you repeat again? Yes. So his question is more on the device side, that one of the reasons we don't use, one of the reasons is we have limitation on this maximum VDS is basically breakdown. So essentially what happens is the maximum, even when you are applying a VGS, there is electric field. And whenever you are applying a VDS, there is an electric field. There's a vertical electric field, there's a lateral electric field. And the value of the electric field cannot really go to infinite, right? Because ultimately you have a lattice underneath, it will break the lattice. So there is a maximum electric field that you can apply. So very often this VDS or the VGS max that you can apply is determined by the breakdown condition of that particular MOSFET. And you should be able to appreciate this because, I mean, these numbers are often touted in the news, that you hear that TSMC is making 3 nanometer MOSFETs, 3 nanometer node, 16 nanometer node, and so on. That number, 3 nanometer, 16 nanometer, or whatever, refers to the length of the channel. So this channel is essentially, this L refers to the technology node that we refer to. When you say 3 nanometer, that L is 3 nanometer. When you say 65 nanometer, that L is 65 nanometer. Similarly, there is a constraint on the thickness of the oxide that you can apply, because if you decrease the thickness, naturally you are increasing the electric field, right? Naturally you are increasing the electric field, which means there is only, if you decrease the thickness, which means the maximum voltage that you can apply between the gate and source is also limited, because you might end up into breakdown, right? So essentially, one reason you would want to reduce these oxide, these thicknesses, because you are getting better gate control. Because if you are reducing thickness, you are increasing Cox, right? From device perspective, if you are increasing thickness, you are increasing Cox, which means for the same value of all the voltages that you can apply, you can get more current. So you are increasing the channel control by increasing thickness. So there is a motivation towards going towards reducing thickness, but if you do that, you also have to reduce the path of voltage because you are going to breakdown. Okay. Okay, fine. We'll meet tomorrow and continue from this.